Hi, everyone. I'm
Good
Sean
evening,
Cooper.
sir.
I'm not a software engineer, which I'm sure that's why you haven't seen me around. So I'm studying motion picture science, which is a major over in the College of Imaging Arts and Sciences, where I study both imaging science, which is more pure science of imaging, and also the artistic side of filmmaking and things like that. So when you guys talked about tech talks, I was like, oh, I guess I know stuff that some people here might not know. So I figured I would just talk to you guys about imaging and general concepts that could possibly help you with imaging applications and things like that. So let's get started. So I'm just going to cover some basic concepts such as the imaging chain, digital imaging, mathematical concepts, processing, dabble in computer vision a little bit, nothing crazy, and then give you a little inspiration, I guess. So when you think of it's very hard to describe a complete imaging system. What is an imaging system? Sometimes it's just a camera, but it can be many things beyond that. So what we tend to do in our industry is describe it with this thing called the imaging chain, whereby there is a source that emits some form of electromagnetic radiation or something else. There's an object which you're trying to perceive or image, and then there's the capture and preparation where you collect, detect, process, store that information, and then display perception. So I'll start with the beginning, which is light. So there's a number of imaging systems, some that you wouldn't even think of as imaging systems, such as your eye, which is the most basic and the foundation of everything imaging. Glasses, camera, projector, scanner, printer, CT scans, MRIs, telescope, holography, and sonar. Sonar is a weird one because it doesn't use light, it uses sound. So I'm going to focus mainly on light imaging systems. So what the heck is light? Light is electromagnetic radiation, obviously. Charged particles or waves flying through space. So what we tend to care about is this range here, 400 to 700 nanometers approximately. So that obviously goes all the way down to gamma rays and then up to microwaves. So there's this wave-particle duality of light, whereby I'm sure you know in your physics classes, light can be described as both a wave and a particle, which this charming young fellow came up with the particle theory of light, Einstein. That's what he got his Nobel Prize for. He was able to make a single photon release a single electron, which sounds easy, but is actually really freaking hard. And that's why Nobel Prize. So going back to the top of the imaging chain, we start with a source. And when you're talking about imaging, at least in a quantitative sense, you have to stop thinking of it in qualitative sense. So like, oh, that looks bluish, or that looks yellowish, or things like that. So when we're looking to imaging systems and looking at the world around us, we look usually in terms of wavelength and what we can see and what's out there. So this is the what's called the spectral power distribution of our sun, which on the x-axis is wavelength, and then on the y-axis is the power, or the output relative. It's normalized. And we can see that our visible range, which is highlighted here, from 400 to 700, is very conveniently the peak distribution of our sun. So possibly from an evolutionary sense, that's why our vision lies there, because it is the peak output of the very near star. So the sun works as what's called a black body, in the sense that it's a heated object which emits a spectrum of light. And the characteristic of this is a very smooth line, as you can see here. But the eye is very easily fooled. We're sitting in a room, and I think you would agree with me that the general color is white. But it's not quite always the case. So there's other kinds of sources of light, things that emit light, such as a tungsten bulb, which when you're sitting in a room, You're like, you look at a piece of paper, you say it's white, even though when you look to the visible spectrum of its output, it's principally in the orange-red side, whereby 400 nanometers would be blue-ish and 700 would be red. So when we look to tungsten bulbs and why they're trying to switch to LEDs and stuff, we see that their peak distribution is actually beyond the visible spectrum into infrared. So energy being put into this tungsten bulb is principally being used for heat infrared. So the switch to LEDs and things like that is just as a side note to increase power efficiency. And there's been other methods such as switching to halogen, which introduces gas and then kind of shifts it a little closer to the visible spectrum, but not quite. So like I said, we're in this room right now, and everyone would agree that the room is bathed in white light. But when you look to fluorescent, it's this crazy, weird, spiky mess, which our eyes visually integrate to create white light. So fluorescence works by, there's phosphors coating a tube and then an electric charge sent through that. And you can see there's peak emissions at different kinds of wavelengths because of these gases, whereby a standard black body, which tungsten or daylight would be a smooth curve. So that's because the reason we perceive it as white is because our eyes integrate over a large amount of wavelengths. So we have 3 cones, small wavelength, medium wavelength, and long wavelength, which most people refer to as blue, green, and red cones, which they cover a large gamut of the spectrum and, like I said, integrate to create a perception of white, whereby there's a roughly equal response on all 3 cones. So onto objects. So objects can only reflect color that is incident upon them. You can't be shining a red light on something and have it look blue, because if there's only red light, it can only reflect red light. So when looking at this thing like a sailplane, it appears to be white. And why does it appear to be white? Because all of the wavelengths are equally reflected off the material. So when you look to the red trailer behind it, it absorbs the green and blue principally, and then reflects red. So I'm just kind of going through this to give you guys a more conceptual understanding of how we perceive the world and how the world looks by our own personal imaging system. And then there's also transmissive objects, which do approximately the same thing, but absorb, to get a yellow color, you absorb blue light, and then red and green is combined in our eyes to give the sensory perception of yellow. So when we look to capture objects, imaging systems, there's a whole range, anything from your cell phone camera up to a high-end DSLR and things like that. Whereas a cell phone camera will principally capture images that are pre-compressed for file size, because obviously you want to take as many pictures of that object next to you as you can. Insert object here. Or you can be more fancy and use your DSLR, which you have the option, usually, if you've noticed, there's like, you can choose JPEG or RAW, whereby if you choose JPEG, it's pre-compressed because that's a compression algorithm. Whereas RAW is saving every pixel value before it is demosaicked, which I will go into in a little bit. So this is just what you'd typically think of as imaging systems, a single capture camera, whereas there's also video, which is nothing that magical, just a series of pictures taken sequentially and very quickly in a timely manner. So again, there's like home camera systems which employ compression, and that can bring in artifacts into your images. Or you can go for a $60,000 Arri Alexa if you're in the mood. Which this is a cinema grade camera which will record in RAW format and introduces as little artifacts as possible, and the whole thing in motion picture now is to give these digital systems a filmic quality, because we've been on film for 100 years now, essentially, and some people still are. So it's a huge quest to give these digital values a visual quality that is akin to film. So another imaging system that you might not be aware of is used quite extensively in our sister major, the imaging science, where they do remote sensing. Remote sensing is imaging things remotely. You don't need to be there pushing the button to take the picture. So there's satellites with imaging systems, the Hubble Space Telescope. You can stick cameras into a plane and fly them over an area. And the interesting thing is most of you guys are used to images having just 3 color channels, red, blue, and green, that relate to the 3 cones in our eyes. Whereby if you're interested in more scientific understanding of the scene that you're imaging, there can be anywhere up to 300 different color swatches, I'll call them, whereby you have a filter over a certain sensor and it's only specific to a certain wavelength. So this is sometimes a one-dimensional camera, whereby it's like a scanner with just one row of pixels, and then they'll fly over an area. But they have 300 rows, or 300 rows of sensors. So with this, you can get a much more detailed understanding of the world around you, or the world below you, in this sense. So this is a more scientific end of imaging, whereby we're more used to the consumer end, where we want to take pictures of our children or our cat and things like that. So moving along to, obviously the end goal of any imaging system is to eventually make it useful to a person in some way. So that is often used by, or done by display, obviously, which is your computer screen, TV, or if you want to do a volumetric display like we did last year and display things in 3D, all the better. So so we want to display data in a useful way. So we can false color information to give us new ways of perceiving things, whereby if someone was just looking at this image, it would just be a matrix of a giant bunch of numbers, and numbers aren't inherently useful to us. So if we need to see the currents and the temperatures of water near continents, we can look and apply this filter whereby certain values are certain colors, and then a human, an end user, can derive useful information out of something like this. So I'm just going to jump into the basics of digital imaging, which, now that I think about it, is kind of useless, because all of us have grown up on digital cameras. We know exactly what they are, or so we think. But I was just going to go into the definition of a digital imaging system is that there's quantization and subsampling, which I'm sure you've heard 1,000 times in other classes that relate to digital systems. So the quantization and subsampling with images is temporal, where there's the shutter speed, where you can integrate over a long period of time, open your shutter, have lots of photons flow in, and then close your shutter, and then read the values off of that. And then there's also spatial subsampling, which would be your pixels. And then also tonal, whereby you can have 3 color channels or 300 color channels at different bit depths, where we're most used to 8-bit, where most people, web designers and such, will think of color as 0 to 255 of red, blue, and green, whereby in such as cinema systems, we can have 12-bit imaging, 12-bit resolution to our color, which infinitely expands your possibilities. Not infinitely, obviously, finitely. So when we look to digital sensors or the physical spatial subsampling, this is the most common sensor type, or not sensor type, but there's a filter overlaid over the sensor. This is called a Bayer filter, whereby a single pixel that you would, if you zoom into Photoshop and you see just one pixel sitting there, it was actually composed of 4 different subpixel elements. And the reason that we have twice the amount of green subpixel elements is because green is most related to our perception of words. Not words, but detail. Because so when employing compression algorithms such as JPEG and things like that, it's generally done in the sense that the green channel is hardly ever touched, or very lightly touched, because it's so responsible for our perception of detail in that image. Whereby, if you look to the human retina, there's very few blue cones and less red cones, which the green cones densely packed gives us a more detailed imaging. So when you spatially subsample space on an imaging plane, you can introduce artifacts. Artifacts being things that show up in your image that didn't exist in the real world. So one example of this is aliasing. Most of you probably know aliasing from that option in your video games, which is anti-aliasing, and you're just, well, I want all of it gone. So what that is, aliasing is whereby is the artifact that occurs where you have a high frequency, but due to the high frequency here is the red wave. And if you sample it at discrete units, 0, 1, 2, 3, 4, it can be presented as being a low frequency signal. So in your video games and things like that, the anti-aliasing gets rid of jaggies, whereby it's a high frequency line, and then you pad the edges to give it the illusion of smoothness. Because in that case, it could actually be the opposite, where it's supposed to be a low frequency signal, a straight line, but because of the subsampling, it appears to be jagged and disjointed, and there's methods of getting rid of that. So when you look to an imaging system, a camera, this shows up 2-dimensionally, and you can kind of see it there. Is there any way to dim the front lights a little bit?
Yes, there's going to be a couple switches right underneath the projector screen.
Oh, below.
No.
Right there.
Ah.
Nope. See, we got these.
Wow.
That's good.
Yeah. I don't know. If you can see it, it kind of looks like a wave. So this is...
Oh, yeah.
That can occur when you're taking a picture of a brick wall with too low of a resolution, so that the high frequency signal, which frequency is viewed in kind of a weird way in imaging, in the fact that each pixel, you think of images as a giant matrix of values. And in most cases, it's a 3-dimensional matrix, in fact that there's length, width, and then depth. And the depth is usually regarded as the color information. So you have one 2-dimensional matrix that has all of the RGB values of red, and then another with all the values of green, and another with all the values of blue. So frequency, in this sense, is if you were to take a slice out of this image and plot the values on a graph. So for this, it would be lower for the darker colors and higher for the brighter colors. So it would be something approximately sinusoidal. So again, when imaged, this effect happens, and then we get this weird waving look. And this can actually be seen with your own eyes. I don't know if you notice when you look through a screen door sometimes, it looks like there's this wavy pattern that appears. That's not on the screen door, that's weird things happening in your eye, which is actually pretty cool to realize that there's a finite limit to our resolving power in the human eye, which was also, that's the reason they can call their displays retina displays with the Mac products, because they've decreased the pixel size so much that our eyes can no longer resolve the pixels, which is actually pretty cool. So jumping to very flowery language and high-level talk about images in the mathematical concepts. So like I said, images are just giant matrices, which for some people helps them like, oh, that makes sense. Because when you look to an image, there's just values. And like I said, there's 3 different planes, or it's a 3-dimensional matrix, whereby each plane is a different color. So when you have a giant matrix of numbers, you can do matrix math, yay. And with that, you can do fun things like rotate an image, yay. But the problem with images is that they're not completely ideal, in the sense that if you were to go into your math class and they'll give you draw a triangle and say, rotate this to rotate it X amount of degrees. And that's fine and dandy because each vertice of that triangle is infinitely small because it's a point. Whereas with images, if you try and do that, there's not individual points of pixels. They have a finite amount of space. They're square. So when you say, I want to take this pixel and rotate it and move it over here, you're like, OK, that's great. But now that's rotated, I actually need 4 pixels because it doesn't quite fit in to where I need to rotate it to. So there's a bunch of different ways to go about doing this mathematically. One of them is bilinear interpolation, which is you look at, it's a pretty simple way of doing it, where each corner here is a pixel, and it has some value. So to get this value that lies between the 4 of them, which there isn't one, you have to create it. So you do it by essentially finding where the point you're looking at, and then you create a linear line between the 2 pixels on each side of it, and then choose the point which aligns it in like the X dimension, and then average between the 2 to give your new pixel. So when you look at it, this is a beautiful child that I happened to pull off. This is a test image that Kodak uses a lot for image processing. So I'll go back. So this is bilinear interpolation, which is just one way. And there's the other way of nearest neighbor, where when you have the problem of, I don't know which pixel to choose, you can just say, just give me the closest one. So that can lead to different implications, such as this is the original image, and then with nearest neighbor, it gets quite blocky because you're just grabbing nearest pixels, which often duplicate themselves, and then you have suddenly 1 pixel becomes the same value but for 4 pixels. So the reason that we went to bicubic or bilinear interpolation was to make it so that the image looks smoother. So this is the original again, and then with bilinear. It's better, but it's a little blurry. So that would be considered an artifact, as with the blockiness in this image. So also with having images just as giant matrices, we can do things such as convolution, which is usually what's done in different applications like Photoshop. Like you want to blur something, you want to sharpen something. Different filters that can be applied to digital images. So a convolution is where you take, it's called a convolution kernel, and you have a tap, which is the center value. And what you do is you take this kernel and run it over your image in what's called a raster pattern, which is you start at top left, scan over to the right, drop down to the next row, and continue scanning and scanning. And when you do that, you grab the value you place the result of this convolution is placed in the center, but you look at the values that surround it. So there's different kinds of kernels we can do to do different things. So if you want to sharpen an image, you want to do edge detection. You want to find, when I'm driving this robot around, I want to know that the edge of the wall is there and not the flat part of the wall, because can't go through that. So you can do what's called a Laplacian filter, where you apply a weight of -4 to the center value, and then 1 to the pixels above, below, and left and right. And there's different orders of magnitude, such as this and these 3. So when you do this, you run a loop over your image, going over the rows and then each column, or go through the columns and then down each row. So the result of running this kind of convolution kernel over an image is something like this, whereby you have an original image and then you run the convolution over it, and then the edges are increased. So if you were trying to find where the edge is with some sort of, let's say, a robot, the edges have been increased or decreased from black or white. So you could do a limit. There's gray values, which if you have a 0 to 255, they'd be like 128, around that range. So you can say, only give me values that are below 10 or above 200. And then suddenly this gray will disappear and you only have data on the edges, which you can then interpret in your algorithms and other things. So, or if you want to do something more specific where you don't want to just find an edge, you want to find a single point, you can do the same thing where you run a convolution kernel over your image and then you just threshold it. So if you want to find a defect in a product that you're analyzing, such as there's product running down an assembly line, you want to see if there's any defects in it. So you do very high speed as it goes down the assembly line, grab a quick picture. Okay, got the picture. Now run this convolution kernel over it, and then you get something like this. It's a little hard to see. But you'll notice that there's a single point which stands out, and that is this right here, which could be a defect in your product. And then you can throw it in the trash and things like that. So, so you can use these filters to, apart from just making you look blurry or make your blurry picture look sharper, you can do more quantitative analysis of your scene. And then probably one of the most useful mathematical tools used in image processing is when we put our images in the Fourier domain. I'm not exactly sure. Is anyone familiar with Fourier mathematics or what the Fourier transform is? A couple people? Okay. So we learned a lot in physics where if you have two waves and you superimpose them or have the two waves going in the same place, they constructively add, where if you have low frequency wave, medium, and high frequency wave, the resultant wave is this strange looking thing. So when we do Fourier analysis, we're usually doing the exact opposite, where we have some signal that exists in the world, whereas this case it would be our image, where you have a black pixel, a gray pixel, or I guess it's going negative. There aren't negative values. But we take our original signal and then we break it down into our component parts, which can be incredibly useful. So when we look to our images, we can take the what's called the Fourier transform of them. And actually, I'm going to pop out of this quickly. Anyway, and show you a quick video I did because I was bored one day during class. I'll drag it over there eventually. This is the video which I called the Fast Fourier Transform of Fantastic Mr. Fox. So I took every frame from this movie and then did the Fourier transform and displayed its magnitude information, where, again, it's a little hard to see. If I bathe you in darkness, it might help. Cool. So when you take a Fourier transform of this image and look at its magnitude information, you get something like this, whereby in the center, I don't know why I keep saying whereby. In the center of the image, you have low frequency information. Low frequency is, in this case, or in the dead center, is a frequency of 0. So that's going to be the mean value of your entire image. So if it's a dark image, this will look dark. And if it's brighter, it'll be bright like this. So there's also other frequency information. You can look at, especially in the bottles of cider, that would be a relatively high frequency at a certain location. So it gets brighter, a little darker in between, brighter, a little darker in between, and those pop up, interestingly, as little dots that you can see here. And that is because its frequency in the x direction or frequency in the y direction on the y-axis, and frequency in the x direction in the x-axis. It's not quite an axis, but I'll just use that for simplification. So you can tell that there's a frequency that is principally in the x-axis, which would pop up in this line here. So I'll just play through this really quickly, and you guys can see what as the image changes, what the image looks like in the frequency domain or the Fourier domain. So hopefully this isn't too loud. I also just happen to like the song, so.
You get how incredible this is?
So actually, from a geeky math sense, that scene in particular is very interesting to me, because when we start zoomed in on the objects, the frequencies are largely low. Low frequencies meaning bigger variation. So the glass bottles, for instance, are larger. So it goes brighter, darker, brighter, darker. So you can see that most of the information lies in the center, which is low frequency. But then when you zoom out with a camera, these objects become smaller. And in a mathematic sense, the frequency becomes greater with a higher frequency. So when you see them zoom into this screen, it almost looks like you're zooming out in the frequency domain, because this low frequency information gets higher. So you'll see points expand. And it's just interesting little quirk of lenses and zooming in. Anyway, I think the point might have come across. Won't play the rest of that. So we can do fun things with, bring the lights back up. We can do fun things in the Fourier domain. We can do faster things too, because it's largely matrix manipulation instead of a very slow loop where you go by pixel, which in some cases these pictures can be absolutely immense, where if you're working in the film industry, for example, they use 8K imaging, which is approximately 32 million pixels that you have to loop over. Whereas if you can do matrix manipulation, things go much faster. So what we do here is we have this image, which actually is very famous among the imaging community. Her name is Lena. She is actually the first digital image ever created, just as a fun little history fact. The first imaging system was essentially a giant like bingo roller kind of thing, where you'd take a piece of paper, roll it over this dome, and there's a single sensor at the top. And it would take a value, you'd rotate a little bit, take a value, rotate a little bit, take another value. So when they first got this thing together in their lab, they're like, oh, great, it should work. Let's test it on something. And they're like, what do we image? And it's like, I don't know. So one of the researchers, he's like, oh, I've got an idea. He runs back to his office and comes back with an issue of Playboy. And he rips out the centerfold and wraps it around the drum. And this is the top half of Lena, the very first digital image. So it's just a fun little bit of history. And I've honestly gone to antique shops trying to find the issue where she's in it, just because it's a bit of imaging history. And actually, it's kind of interesting also, if you look at the first 2 or 3 rows in the image, it's exactly the same. That's because they're like, okay, it's scanning. Yeah, cool. And then a little while later, they noticed, oh, wait, the sensor isn't moving at all. So they scanned the first line 3 times before they realized that the thing was working. So they give it a good kick, and then it kept going. Anyway, back to Fourier domain. So when you take a Fourier transform, you'll get something that looked like the bottom image that I showed you in the video. So if you want to do something like blur an image, we can do a low-pass filter where you let the low frequencies through, whereas detail is in the high frequencies. So if we do a threshold where we say frequencies beyond this point are zeroed out, and then we only pass the low frequency, and then we do the inverse Fourier transform, you get something that looks like this. It's a little less than ideal because, as you can see, there's actually low frequency artifacts in it. I don't know if you can actually see it, but it looks a little wavy. It almost looks like a Zen garden kind of thing where you drag the rake through the rocks. And then you can also do the exact opposite, where you have a high-pass filter. So if you have this original image, you take the Fourier transform, you threshold it where you only use high-frequency information and get rid of the low frequency, and you get a really nice edge detector. So we can use these things for things like computer vision. I didn't really have anything to throw up here on that, but basically when you do computer vision, all you're doing is standard digital image processing, but usually to video, and you also try and optimize it so it goes really, really fast. Because I've written many algorithms to process images, which for a single image, which was only like 400 by 400 pixels, have taken like 3 hours. And granted, that was a little more complicated than what you'd normally be doing for your image processing applications. But still, it shows that when you're doing especially loop iteration, you can get really slow performance. And so computer vision, the big thing, such as with OpenCV, where they use C libraries and things like that to make image processing going really fast. And also, it's interesting with computer vision because sometimes there's no end user. It's not capture something, process it, and put it on display so you can be like, oh, yes, that's very interesting. Instead, you have an image captured, processed, and thresholded or put in Fourier Domain or things like that, and then interpreted by a computer and acted upon by some machine of some sort. So imaging and computer vision is found everywhere, such as the Curiosity rover, which has a stereoscopic and many other imaging systems, which actually there's a lot of interesting things in there that I can go into later. Computer vision such as augmented reality, whereby if you look through this image, you can identify objects and their position and then overlay 3D graphics onto it. And actually, I found this interesting, is that you can also do, obviously, like face detection. I'm sure you're aware that exists. And there's also people working against it, where there's different layups of makeup that you can add to your face to thwart face detection and things like that. So at this point, I really just welcome questions, because if any one of you have anything to ask, I'm kind of zipped through stuff pretty quickly, and I'm sure most of it went over your head and also mine. So if anyone has any questions about any imaging applications that they know or are curious how they work, I could probably talk to that next time. Cool. Okay, so if you guys have any other questions about imaging, image processing, you can talk to me, where I can probably get in a little more depth. I was just trying to get a conceptual understanding. Or there's an entire department, the Imaging Science Center, which is the Carlson building, and then also my major, which is motion picture science, and our chair is David Long, and we're found in the basement of CIAS. So I'm also just trying to make you guys aware that if you're trying to do imaging applications and things like that, there is an entire research center here that could help you with your projects and things like that. And I would love to help as well. So on that note, thank you.